The picture opens with a burst of light in a technical log and a flurry on social feeds. Fresh images, a jet of dust and gas that seems to aim not away from the sun but strangely toward it. That single counterintuitive frame, caught in the waning hours before our telescopes lose sight, turns routine observation into a question that refuses to be polite. Why does this visitor, cataloged simply as 3 Atlas, not behave like the comets we thought we knew? The images arrive like a challenge. Was that forward-facing streak an ordinary dust jet sculpted by sunlight and rotation, or a fingerprint of something we have never before collected from the void? This moment, bright and brittle, is why we lean in. The timeline is maddeningly compact. On July 1st, 2025, an automated survey telescope in Rio Hurtado, Chile, one of the Atlas units designed to spot incoming hazards, flagged a faint, fast-moving object. In hours and days that followed, telescopes worldwide confirmed the motion. The path is hyperbolic. The speed carries the signature of an origin beyond our solar system, and the object is designated 3I Atlas, the third confirmed interstellar interloper we have recorded. The news spread through mailing lists, observatory queues, and later through the breathless cadence of broadcasters. What began as a discovery alert became an international watch. To make sense of its path, we need to slow down and picture orbital mechanics as a kind of cosmic freeway. Most bodies in our sky circle the sun in familiar lanes, near the plane of the planets we call the ecliptic. 3I Atlas, unusually, arrives with a trajectory that lies roughly in that planetary plane, an odd choice for an interstellar voyager. Its inbound speed, calculated from radar and astrometry, places it on an open, hyperbolic track. It is not bound to the sun the way Earth or Jupiter is. Perihelion, its moment of closest approach to the sun, arrives at the end of October 2025 at a distance on the order of a little more than 1 astronomical unit, outside Earth's orbit, but close enough to experience intense solar heating. That perihelion is not just a date on a calendar. In orbital physics, it is the point where the sun's gravity and the object's velocity conspire to offer the greatest leverage on motion. Spacecraft engineers call the Oberth effect the sharp advantage of burning your engines at perihelion. Analogously, anything that ejects mass or experiences solar impulse near that point sees an outsized change in its trajectory, which is why observers speak of late October as a make-or-break window. But small actions, natural jets of gas, or hypothetical engineered thrusts, could produce outsized, detectable changes in course. Before the blackout that comes with close solar geometry, telescopes assembled a dossier. Photometry showed a rapidly brightening coma. Depending on whether that light comes from a solid nucleus or a haze of dust, size estimates bounce wildly. Spectroscopy hinted at volatiles and minerals, signatures consistent with water ice and carbonaceous compounds, but also some spectral oddities that prompt second passes and careful modeling. Polarimetric measurements carried out at several observatories suggested light scattered in ways that are not identical to classical solar system comets, an observational tension that pushes scientists into careful, sometimes uncomfortable debate about instrument sensitivity, viewing geometry, and interpretation. Spin data derived from subtle changes in the coma's brightness pointed to rotational modulation and possible fragmentation. And crucially, during a close approach geometry, the object swept relatively near Mars, prompting orbiters and Mars-based instruments to point their eyes and radios in hopes of local information. The combined mosaic, brightness inconsistent with simple size assumptions, exotic spectral hints, and spinning jets, created a pile of anomalies that demanded rigorous accounting. Then came the blackout. As the object slipped toward perihelion, it followed an arc that placed it for a period in the sun's glare from Earth's vantage. When a target sits within a few degrees of the sun, its faint light is overwhelmed, and ground-based telescopes simply cannot see it. Even many space telescopes are constrained by thermal and pointing limits. That darkness is not just an inconvenience, it is a window during which rapid changes could occur unseen. A dramatic outgassing event, a fragmentation, or less likely but more dramatic, a brief thrust or ejection could happen while our instruments stare elsewhere. In practical terms, the blackout creates an observational gap that amplifies uncertainty. What we know before perihelion may be altered by unseen events at perihelion, and what we see afterward must be interpreted with the possibility that the object has been modified while unobserved. Faced with the unknown, the community has organized two broad working hypotheses, one conservative, grounded in decades of cometary science, the other provocative, demanding more extraordinary evidence. Hypothesis A treats 3 Atlas as a natural, porous body, a comet or fragment from a protoplanetary disk, perhaps formed in a different chemical environment than our own, and thus carrying unfamiliar signatures. Under this model, we expect perihelion to trigger intense sublimation, surges in gas and dust production, the formation of multiple jets, and possible fragmentation into smaller pieces that would expand the coma and modify brightness in predictable ways. Non-gravitational accelerations, if measured, would correlate with mass loss rates and the timing of outgassing. Spectra should show a mixture of volatiles like water, carbon monoxide, and more complex organics typical of cometary nuclei, and polarimetric signatures will fit models of irregular dust aggregates. If perihelion produces more dust than expected, the inferred nucleus size will shrink and estimated mass will adjust downward, resolving some of the pre-perihelion tension between bright appearance and weak gravitational influence. Hypothesis B entertains the engineered probe possibility. This is not the default, and it is not accepted without extraordinary evidence. Nevertheless, a minority of researchers have articulated clear predictions so that the proposition can be tested and, crucially, falsified. If some part of 3I Atlas were engineered or carrying technological components, the post-perihelion fingerprints would include sustained non-gravitational acceleration inconsistent with volatile-driven jets, narrow-spectrum emissions or radio signatures not explained by physical ejection of dust, and perhaps the asymmetric release of small secondary objects with controlled trajectories. Spectroscopy might reveal industrial compounds or anomalous element ratios that do not fit known cosmic chemistry. Polarimetry could return patterns inconsistent with problem-free dust scattering. Importantly, proponents of this model emphasize the need to search for repeatable, directional signals and to rule out more mundane but subtle natural explanations because the bar for claiming engineering is necessarily high. So how do we test these competing views? The post-perihelion checklist is essentially a falsification kit. First, precise astrometry. Measure tiny deviations from the gravitationally predicted track and compare them with models of outgassing. If accelerations match mass loss patterns correlated in time with spectroscopically detected gas species, that supports the natural hypothesis. If accelerations persist without corresponding outgassing signatures, the engineered hypothesis survives scrutiny. Second, time-resolved spectroscopy. Repeatable detection of unexpected compounds, especially those generally produced only industrially on Earth, would be startling, but such claims must survive cross-instrument scrutiny and laboratory analogs. Third, radio and active sensing. Targeted radio observations, including opportunistic use of spacecraft assets when feasible, can reveal narrowband emissions or structured radio noise. A null result rules out simple active transmissions, but not all forms of engineering. Fourth, direct imaging resolution. Any resolved structure or persistent secondary bodies would favor complex scenarios. Each of these tests is measurable and, crucially, falsifiable. They allow the community to move beyond speculation to evidence. The human story runs through every technical line. Teams at observatories in Hawaii, Chile, La Palma, and in orbit move like firefighters, on call, trading email subject lines, pushing proposals, and retasking instruments. Coordinating bodies such as the International Asteroid Warning Network have stood up campaigns to consolidate astrometry and photometry so trajectory uncertainties drop and every centimeter per second of velocity can be accounted for. Meanwhile, individual scientists, lid scientist name, who sleeps poorly because the next clear night could be decisive. An instrument scientist at a Mars orbiter who wakes to a query and pushes a cued observation forward carry the hope and responsibility of the experiment. On the public side, sensational claims spread quickly. Social feeds juxtapose sober observatory press releases with grainy videos and conspiracy threads. The scientific institutions respond with careful language. Data are shared, uncertainties are explicit, and extraordinary claims are tempered by the communal insistence on reproducibility. That tension, the slow, meticulous grind of analysis versus the human appetite for narrative, becomes its own kind of drama. Policy matters too. If the object shows any anomalous behavior suggestive of directed emission or intelligent design, the conversation shifts beyond journals and telescopes to international agencies, planetary defense networks, diplomatic channels, and protocols for responsible communication. The community has learned from past near-miss events that transparency, careful risk assessment, and international coordination are essential. But the more immediate policy action is mundane and practical: allocation of telescope time, approval for spacecraft opportunistic observations, and clear lines for community vetting of any claim that would upend the standard model of cometary science. In short, the scientific response is also a bureaucratic one, and those two gears must mesh quickly and fairly. After perihelion, the world will watch the data roll in with a mix of hope and procedural patience. If the post-perihelion astrometry aligns cleanly with volatile-driven models and spectroscopy reads as expected for exotic but natural materials, we will have learned something profound about the diversity of planetary systems, and one more interstellar messenger will have returned to the galaxy with secrets about formation and chemistry. If instead we find persistent unexplained acceleration, structured radio signals, or industrial-like spectral lines, the stakes rise dramatically. The claim of engineering would not only rewrite parts of astrophysics, but would demand immediate coordination across agencies to interpret and respond. Either outcome is a scientific triumph. The former because it expands our taxonomy of natural phenomena, the latter because it forces a disciplined global conversation about evidence, interpretation, and the meaning of encountering something outside our experience. Visually, the story is full of haunting images. Imagine a faint, fuzzy orb crowned by a spiky coma, its jets like a dancer's hair in a sudden wind. Imagine data plots, residuals and position angles flickering across an analyst's screen. Imagine a Mars orbiter, its camera trained for a brief window, returning frames that will be compared pixel by pixel. And beyond the instruments lies the human tableau. A lead observer sipping coffee at dawn as a telescopic dome opens, a network operations center receiving a late-night burst of astrometric observations, a coordinator emailing a worldwide list asking for photometry in a narrow filter. These are the small, domestic images that make the cosmic drama legible. The coda is sober. No evidence so far indicates any danger to Earth. 3I Atlas's trajectory does not intersect our planet, and its closest approaches are far outside collision risk. What this encounter offers, however, is a rare laboratory, a chance to study material forged elsewhere, to test our physical theories under conditions we cannot reproduce, and to refine the instruments and international cooperation we will need for truly consequential decisions. Whether 3I Atlas turns out to be a spectacularly odd comet or the first object to force us to consider technological origins, the obligation remains the same: gather data, weigh evidence, and subject conclusions to the community's peer-based scrutiny. Tonight, as telescopes prepare for another sweep and orbiters cue their instruments, the image that opened our story hangs in the air, a forward-facing jet that asks plainly, what happens next? We do not answer yet with certainty, only with method. We wait for numbers, for spectra, for position angles to converge. We watch not because we crave a story, but because the universe has handed us a question we can test. The best way to respect that gift is to let the data speak and to be ready, together, to listen.